Hello, everybody, and welcome to this new appointment with the IAC General Seminars. It's a great pleasure to have with us today Professor Irène Gijbels. Irène Gijbels is a senior full professor at the Department of Mathematics of the Catholic University of Leuven. In 1990, she took her PhD thesis in mathematical statistics under the supervision of Professor Vera Verbeke. In 1992, she spent 5 months as visiting professor at the Department of Statistics, University of North Carolina at Chapel Hill, USA. Her main research interest is in mathematical statistics, statistical inference, asymptotic theory, non- and semi-parametric estimation of regression functions and surfaces, with applications to change point detection, edge detection, and surface reconstruction, study of dependencies via copulas. She has been member of the Pearson Prize Committee in 2015 to select the Carl Pearson Prize for Contemporary Research Contribution of the International Statistical Institute, member of the Committee for the Prize Pierre-Simon de Laplace de la Société Française de Statistique in 2019 and 2022, and she is member of the Publication Committee of the Bernoulli Society since 2020. Moreover, she is fellow of the Institute of Mathematical Statistics for fundamental contributions to the field of non-parametric statistics, especially non-parametric smoothing, change point, and non-parametric survival analysis, and for her invaluable services to the profession. Since 2006, she is a fellow of the American Statistical Society and fellow of the International Statistical Institute. She has been associated editor of various journals, such as Electronic Journal of Statistics, Journal of the American Statistical Association, the Annals of Statistics, Statistica Stinica, Journal of Computation and Graphical Statistica, just to cite some. She has been the PI of different research grants, and she has been the PhD supervisor of more than 25 students, and she published more than 140 papers in statistical JCR journals. Thank you, Irène, for being with us. And now I think we can start.
Thank you very much, Italia, for this very nice introduction. So welcome to everybody. Well, the talk that I'm presenting today is in some sense a bit special because it's survival analysis, and it's about recent work that I did in that area. And it's joint work with Anneleen van Rasselt, who is at the University of Hasselt in Belgium, and one of our former PhD students, Worku and Metu. I will start very easygoing, I think, in this topic because it's hot outside and it's July. And I'll start first of all by just introducing you what is survival analysis and what are the common regression models before going to this hybrid hazard-based regression models, talk about the ingredients that we have there, say something about statistical inference, and also testing hypothesis, give you a real data example, and then conclude. Okay, so what is survival analysis, or what is the big aim when you work in this area? That is, first of all, that you have an event that interests you. And I present that event by a random variable t, which is typically non-negative. And you can think of t when you are in medical sciences as the time till death or infarction, or the time till remission if you have a certain disease. When you think in terms of reliability theory or in terms of engineering, you might think of t as being the time till failure of a technical device. And when you are working in economics, you might think of t as being the duration of an employment period. So the event of interest then would be getting from unemployment state to an employment state. So t, let's say the event of interest, is presented by this random variable, non-negative. Now, typically in survival analysis is that for each of the subjects under study, or each of the individual understudies, you might not observe t. So you have the issue of partial observations. And there are various mechanisms for getting to partial observations. Like, for example, you might know that t, which is your time of interest, would be bigger or equal to c, and you might observe c and not t. That is what we call right censoring. Or you might have the setting that t, your variable of interest, is less or equal to c, and you observe c, that is less censoring. Or in certain other settings, you might have that you know that t is falling into a time interval L and R, and you observe L and R, and that's what we call interval censoring. Now, for the talk today, I will just focus on right random censoring. Why? Because that's the kind of censoring scheme that is still most often, I think, of interest for applications. So let me explain to you a bit more what is right random censoring. So suppose that you have, look at the left panel here. Suppose that you have a medical study, for example, starting in 2000 and finishing in 2020. That would be the end of the study. And you would have that patients, individuals, of course, entered the study in a kind of random way. For example, if you take the first horizontal line here, that indicates a patient that came in a bit after 2000. And just before the end of the study, the failure event happened. So T happened and you observe T. This we call an uncensored observation. If you look at the line above, another patient came in a bit later, but was still like in a very good health, and the event T didn't happen at the end of the study. And that for that one, then you only know that T is bigger or equal to that time C that you observed. And that's a censored observation, which I indicate on the right panel here with the red bullet. So you have uncensored observations, those for those individuals you observe, your time of interest T, and for the red ones you have partial observations. And so if I put that in a mathematical framework, this means that instead of observing T, which is the variable of interest, which I call the survival time, what you actually observe is the minimum between T and C, the survival time and the censoring time, which I will denote Y on the slides. And of course, you know whether you have observed the survival time or the censoring time. And so delta is a censoring indicator. It's 1 if you have observed actually T, and it's 0 if you only know that T is bigger than C. So that's the setting. Now, important in survival analysis is that you know that we have some kind of important concepts with which we work all the time. And I listed them here, the 3 of them here. So the first one, that concept that is important is the survival function. Now, what is that? That is the probability that T, the event, takes place later than the time point small t. So you survive longer than t, let's say, or your technical device is still working beyond the time little t. So that's the survival function. And that's actually just 1 minus the cumulative distribution function, which is attached to t, which is this capital F. And then another concept that is extremely important in survival analysis is the notion of hazard function, also called the risk function, also called the hazard rate, also called the instantaneous rate of failure, which is the following. Given that the event has not happened at the time point small t, what is the probability that in the moment just after that the event happened? So that's the instantaneous rate of failure, if you want to call it like that. And then you have the cumulative measure of that, which is called the cumulative hazard function, which I will denote by a capital lambda on the slides. Now, the nice thing in survival analysis is also that these quantities, you can move from the hazard function to the survival function and the way back. So, for example, the hazard function for a continuous t, I should say, is linked to the density function f of t and 1 minus f by this simpler relationship which you see here at the end of the slide. And if you then recall that the density function is a derivative of the cumulative distribution function, you basically see that the hazard function is minus the derivative of the logarithm of the survival function. And then, of course, you have immediately also the relationship with the you immediately also have the relationship with the cumulative hazard function. I'm not sure whether you see the last line of the slides. I think you do. And so it's important to realize that you can move from one of these concepts to the other one in a very specific way, as is indicated here. Now, often in in reality, we observe not only we have t, but we also often have explanatory variables or possibly predictor factors. And this, of course, is bringing us to the setting where you have that covariates are involved. So I'm not only like trying to attempt to observe t, but there is also like the age of a patient, whether there were previous treatments, what is the medical history of somebody. So that information you can measure for an individual under study, and that you can all put together in this bold X, which is the vector of covariates. If this is only a unidimensional vector, then you are in a univariate case, and then I would note with X, which is not bold. But this is the regression setting, which I call the regression setting, right? And in this regression setting, you can actually also extend the quantities which are here in the left column, which I defined on the previous slide. You can basically very easily define them in this conditional situation. Conditional meaning that I know that I have observed somebody who has age or is in that age group, or somebody who has had previous treatments or not. So all that information you put in this conditional argument over here. So instead of having the probabilities as before, you now formulate everything in terms of these conditional probabilities, and that gives you the conditional survival function, the conditional hazard function, and the conditional cumulative hazard function. And in fact, in this talk, I'm particularly interested in this regression setting. Okay, now in this regression setting, in survival analysis, there are two, well, at least two, let's say, very important and very classical regression models that have been put on the forefront and which are there for 50 years and which are still like highly used in applications. And I'll explain these to you before I move on to actually the topic of the talk today. So a first model is Cox proportional hazards model, and that dates back to a paper by Sir David Cox in 1972. And it says the following. It actually models the conditional survival function for an individual, which comes with a value of the covariates, which is equal to little x. It modeled that as a kind of baseline hazard function, which is the same for all patients or individuals in the study, no matter which age they are, no matter which previous treatment that they had, times a factor and that factor purely depends on the covariates. So it's really separating these two issues. So this we call a baseline hazard function, and that is the effect of the covariates on the conditional hazard function. And why is this called the proportional hazards model? Because if you would take two different individuals, let's say one comes with his or her covariate vector x, and the other one comes with the covariate function x tilde. Under this model, you do have that the ratio of these two conditional hazard functions is actually something which is not depending on the time anymore. So it's constant in t and only actually depending on the values taken by x and x tilde. And that's why this model is called the proportional hazards model. Now, the only thing I want to mention further about this is that once you have this model for the conditional hazard function, you can also re-express that in terms of the conditional distribution function, the conditional survival function, how this relates to the survival function linked with the baseline model that you have, of the baseline hazard function that you have. And these are these expressions. It's not important that you look at them. It's only important that you realize that the model I can actually re-express in terms of either the conditional survival function or the conditional cumulative survival function. Now, on the next slide, I'll show you just a plot of an example of such a model where you do have these proportional hazards. So I had a baseline hazard function, which is the green one. So it's in function of the time. And I took a situation of a univariate covariate to make it simple and to be able to draw it easily. I took 3 different values of the univariate x, and actually the conditional hazard functions for these 4 individuals, if you want, where the green one is the baseline individual, they look like that under this particular kind of under this particular kind of proportional hazards model. So the Cox proportional hazard model, as Cox proposed it almost or more than 50 years ago, consists of the following arguments. Sorry for that. It consists It consists of a baseline hazard function lambda 0 of t, which was left unspecified in Cox proportional hazards model, and it also depends on beta, which are the regression coefficients, and which essentially explain how each of the covariates actually influences the conditional hazard function in a linear way. That's important to realize because this is a linear form, right? And so this was the Cox proportional hazards model. Let me now move to a next very popular and very well-known and very well-used regression model in the context of survival analysis, which is the accelerated failure time model. And it also dates back more than 30 years and even a bit of years before that. And let me explain to you what this model is. So think of T0 as the survival time of an individual in a reference context, right? So when, let's say, x is equal to 0. Then in this kind of model, you assume that the survival time t of an individual which comes in with a vector of covariates small x, that this time t for that individual is actually given by t0 divided by the exponential of x transpose beta, which means that effectively, if this exponential factor is smaller than 1, that the survival time of that individual which comes with this covariate value x is bigger than the reference one, and if that factor is bigger than 1, it's the other way around. So the covariates have an effect in accelerating or slowing down, if you want, the survival time of an individual in a similar kind of linear way, because this is also linear. Now, again, you can write down what is the relationship between the density functions of these two. You can write down what is the relationship in terms of cumulative distribution function, which leads you to writing down this model in terms of the conditional hazard function. And you see that this factor, exponential x transpose beta, is coming in 2 instances. It's coming in as a kind of slowing down or accelerating the time scale in the baseline hazard function, but it also has this multiplicative effect on the relative hazard itself. And you can again re-express then, and that is what is mentioned on the last line of the slide, you can again re-express that in terms of the cumulative hazard functions or the survival functions. So you can move from one to the other quite easily. Now, this is a picture of, to show you the difference between the two models. So I took one specific kind of baseline model, and I then put on top of that either a proportional hazards model, which is the left column of pictures that you have, or an accelerated failure time model, which is the right column of the the pictures here. Again, I took 3 values for univariate covariate, and there is the baseline hazard function, which is in green. So this is the picture that you saw before, but under an accelerated failure time model, it looks very different for the hazard functions. If I show you the picture of the survival functions, that is when you have the difference between the survival functions of these 4 individuals, like the reference one, baseline, and these 3 others. That is what you see here in the bottom panel on the right when I assume a proportional hazards model, and on the left when the other way around, on the left when I have a proportional hazards model, and on the right when I assume this accelerated failure time model. So you see that it's quite different. And of course, this also means that you should realize that, of course, you start with assuming that this model, when you assume it, either a proportional hazards model or an accelerated failure time model, you assume these models to be correct, and then you start doing estimations of the betas, and essentially you want to draw some conclusions. Now, if I put this a bit more in a broader framework, then it is important, I try to summarize it in this small table here in the beginning. So under a proportional hazards model, you have, in terms of the conditional hazard functions, this kind of modeling. So you have proportionality of the hazard functions. Under an accelerated failure time model, you have the effect of the covariates coming in on 2 levels, on the time scale of the baseline covariate, and also on the relative hazard. And there is something which is in between these two, which is the accelerated hazard model, where essentially you only assume that the covariates influence the time scale of the baseline hazard. Now, the thing is that these models, they are very popular, but they are also sometimes too simple. There are many examples around in real data applications where it is clear that Cox proportional hazards model is not valid, so you should not work with it. Similarly for the accelerated failure time model. But due to the fact that they are very, that they are very popular models, we are still using them because they are so nice to work with, but people have been searching for ways to essentially try to adapt them into the more complex situation in which you are often faced with in reality, of course. And so one of the first, among the first ways to do that is by, in the accelerated failure time model, instead of assuming that the effect of the covariates on the time scale and on the relative hazard, as you can see in the second line here on this in this table, is the same, you allow them to be different. So we have a beta 1 and a beta 2 here, which makes sense. There is no reason why you would have to assume a priori that they are the same. So this was done by in a paper in 2001 by Cheng and Jewell. And then about 4 years ago, 3 or 4 years ago, other colleagues basically extended this further in the sense that it's possible that if you, and I give an example now, suppose you have 20 predicting factors or potentially predicting factors. Nobody, of course, there is nothing to assume that the same subset of them actually influences the time scale of the baseline hazard and the relative hazard. They can be different. And so allowing here to have X1 and X2, which are subsets for X, is also important. Now, these authors did that, stepping away from lambda 0 to be fully unspecified. They worked with an exponentiated Weibel regression model here. And what is important to realize is that this is still quite restrictive in the sense that this is a linear effect. The covariates are assumed to have a linear effect on the conditional hazard function, of course, through this exponential factor. And similarly here, that's one restriction which is not always satisfied. I mean, for some of the covariates this might be true, but for some not. And in addition, the fact that they only allow in their procedure to work with an exponentiated Weibull distribution appear to be a bit too restrictive. And that brings me to the point where, which is actually the topic of my talk, is that what we essentially did in our recent work is that we stepped away from this linearity assumption in these two on these two levels, right? And that's one thing. And the other thing, what we did is that we worked with a parametric baseline model. So that's different from what was done in the original Cox proportional hazards model, because if you would lambda naught take here to be non-parametric, this would be too much to handle in some sense. So it would be, this would go one step too far, I think. And so we stick to a parametric model for the baseline hazard function. That's why I put the theta here, and I'll explain to you which is the flexible parametric model that we are working with. And so essentially lambda 0 will be parametrized in a way by theta, and I'll explain that on the next slide. And for this, we basically don't want to restrict to a linear model, except when, of course, from the application side, or when you have a strong motivation for doing that, then of course you should do that. So that's the model, and of course, as before, you can re-express that in terms of the cumulative hazard function and the survival function as over here, but you actually don't have to look at that. So let me now explain what we take for a parametric baseline hazard. And one of the crucial things is that you have enough flexibility there. So you want to work parametrically, but at the same time, you want to be to have a parametric setting which still allows you to have very different shapes in terms of the baseline hazard function. And I'll now explain to you what we use for that, right? What we use for that, for this baseline hazard, is a kind of family of two-piece distributions. And I'll try to explain to you what I mean by that. So remember that we are in this right random censorship context where we have the variable of interest is t, but we don't observe t, we observe y and delta, right? The variable of interest is t. Now, t is non-negative, right? Let me step away for a moment from t, and let me model how I would model a random variable z, which is defined on the whole real line. So which z takes on positive and negative values. And we consider for z two-piece, skewed two-piece densities. And I'll show you a picture on the next slide. But essentially what it means is that you start from a unimodal symmetric density. Think of a standard normal density. Think of a logistic density, for example. Think of a Cauchy density. Think of a student T density. That's this F0. And now essentially you want to make from this unimodal symmetric density something which is skew. And the way how you can do that is as follows. You have a location parameter mu. To the left of mu, you use a different scale for that density F0. And to the right of mu, you take another scale function, a scale parameter of that function. So it's like gluing two pieces of, let's say, if I take F0 standard normal, it's like you take two different standard normal densities of different scales and you glue them together in a continuous way. And you do that with certain parameters. So what are the parameters coming up in this family? The location parameter mu, which is in an element of real line. You have a scale parameter phi, which is strictly positive. And you have a skewing parameter alpha, which takes values into 0 and 1. Now, if you look at this formula and you take alpha equal to a half, then you fall back again on F0. So alpha equal to a half means that your density is a symmetric density and the one with which you started, if you want. Okay, so that's summarized also on the next slide. So alpha is a parameter of your family. When it's a half, you have a symmetric around mu density. When it's bigger than a half, you have something which is left skewed. And when you have alpha smaller than a half, you have something which is right skewed. And for this family, these kind of two-piece families, by the way, they go way back in time, but you have different parameterizations. And the parameterization that I showed you on the previous slide is actually one for which we were able to establish all statistical inference results of interest, like asymptotic normality, consistency, for a very general class of functions f0 satisfying, certain conditions. So it's a family which we have studied in detail, and of which we know how flexible it is, and that's the reason why we basically brought it, are also using it here. Here I'm showing you an example of this F alpha, where I took for simplicity mu and phi 0 and 1. And so I start from a standard normal density, which is the blue curve that you see here. So this is F naught. And if I just take different values of alpha, for example, if I take alpha less than a half and I take three different values, well, two different values, you get actually to these skew to the right two distributions in solid line type, the red and the blue, or the red and the black, I should say. And if you take values of alpha bigger than a half, then you get something which is the dashed lines, and so they are skewed to the other side. And so you see the flexibility by bringing in that. Of course, this is the model that I can use when your density or your variable takes on values on the whole real line, but t was non-negative. So how do we put that into our methodology for t? Well, that's actually quite simple, because you could think of t to be the exponential of z, right? And t is positive. Doesn't have to be the exponential. So there is another ingredient coming in here, which is what we call the function g. You can think of it as a link function, but it's a function that goes from 0 infinity to r, which should be increasing and differentiable, where the first derivative I denote by g prime. And effectively t I denote as g minus 1 of z. So for z, we take this parametric model which I described to you on the previous slide. So this two-piece asymmetric two-piece distributions, and then t you just take as g, the inverse of g of z. And then you can write down what is the density of t under this model, and you get actually a kind of expression, this kind of two-piece expression. But now there is in addition this function g appearing and its derivative appearing. And I should say that the parameter eta is coming in, which is linked with mu via this inverse link function. And effectively, when you have this model, you can write down what is the cumulative distribution function, what is the hazard function, what is the survival function. The expressions for these are actually quite easy to write down, and I'll show them to you on the next slide, but effectively you even don't have to read them. But important is to realize that this choice of this density for t depends on the pair f0g, right? You have to choose that. And what I will try to explain to you on the next slides is that even if you take f0 and g to be fixed, given, you still have quite a lot of flexibility in terms of shapes for the hazard function. So that's crucial. To show you that the expressions for the quantile function, for the hazard function, for the survival functions are easily there. And you imagine you have f0g chosen and you've estimated all the parameters. So as soon as I've done that, you have all the expressions. If you want me to show you the hazard function, I do it. If you want me to show you the estimated survival function, you can easily do it. That's the only aim of the fact that I included this transparency here. Now, why is this model flexible enough, right? Why is this baseline hazard function flexible enough? Well, I'll show you on the next couple of slides for two link functions. I'll show you what different kind of shapes you can have for the hazard function. But let me first of all show you what are the typical link functions that we use in our applications, right? We use the logarithm link. Think of a log logistic distribution, log normal. All this is actually included in the model which I showed to you. Or you can think of a logic of any type of cumulative distribution function fg. For example, you can think of a cumulative distribution function of an exponential function which has a parameter lambda that leads to this link function. For different values of lambda, you get different link functions. And important to realize is that if the link function comes with a parameter, I can do the estimation of that parameter at the same time as all the other parameters. That's also important. Okay, now I come to the fact of why is it flexible enough? And I'll show you for one single F0, a logistic density, I'll show you the different shapes that you can get for some different shapes. I cannot show you all, of course. When you take a log link function, that on the left panel, I always show you some plots for the possible hazard functions by taking different parameters, phi and alpha and eta, right? Because they are parameters that you estimate. And on the right-hand side, I always show you the corresponding survival functions, right? So here you see, for example, for F0 with a log link for different parameters that you can have a decreasing hazard function, that you can have a unimodal hazard function of different shapes. Okay, this is for a log link function. Let me now go to a logit link function. And then it becomes even more flexible because I have this extra parameter lambda. So I'll just show you, so this is the hazard function for different values of the parameters. These are still different functions, and you see that you can have a constant hazard function, you can have a decreasing one, you have an increasing one, you have above touch kind of hazard function. So you have different shapes of hazard functions within one and the same pair F0G that you choose. And that is crucially important. So it gives you a lot of flexibility. Okay, I hope it is clear so far. If you would listening to me live, I would ask you whether you have any questions to ask. Of course, you can still drop a question into the chat box. But so let me come back to the estimation of the parameters from the baseline hazard function, right? So there is originally a parameter mu that changed into eta when I introduced this link function. There is phi and there is alpha. These are, as you can see, alpha only takes values in 0, 1. Now, if I have to estimate that, I have to take these constraints into account. I can do that, right? But we took a somewhat easier way in the sense that instead of estimating lambda, we estimate theta 3, which is the logarithm of alpha divided by 1 minus alpha. And that takes values in R. Similarly, instead of estimating phi, we estimate the logarithm of phi, which I call theta 2, and that takes values in R. Similarly, theta 1 is actually going back to mu, that takes values in R. And we estimate theta 1, theta 2, theta 3, and of course you can easily go back to that, right? Once that I've estimated theta 2, phi is just the exponential of the estimate of theta 2. And so remember, excuse me, that the parameters in the baseline hazard that I need to estimate is this bold theta. Okay, now I'm coming back, putting everything together. So I have this hybrid, excuse me, hazard-based regression model. There is the parameter theta from this baseline hazard, this flexible modeling. And there is the effect of a subset of the covariates on the time scale of the covariate. And there is the effect of the subset of the possible subset of the covariates on the relative hazard. And of course, now what is the aim is to estimate theta, estimate this, estimate that. Once I have that, you have all estimated the conditional hazard function, the conditional survival function, the conditional quantile function, whatever you want. Okay. Of course, it's important to realize that if I would assume linear models for these, I'm back at the model which was studied by Rubin and his colleagues. But of course, I want somehow the data to decide for me whether there is an appropriate parametric model or whether I cannot specify an appropriate parametric model, and then I would work non-parametrically. And of course, what I have are, I assume that I have IID observations of the setting, which means that I have the probabilistic ingredients, which are y. Y is the minimum between t and c. T is my variable of interest. Delta is the censoring indicator, and x is my set of covariates. And I assume that I have IID observations of that, and that the sample size is m. Okay. Now, if you have that, and you want to start doing statistical inference, and you have to, and suppose that you are in a fully parametric way, then the first thing I would do is like setting up a likelihood function. And if you do this, you in survival analysis, there are some typical assumptions which you also always make, and I will comment on these later on. That is that in the regression setting, you assume that for the proportional hazards model, for example, you assume that the survival time and the censoring time are independent of each other, conditionally upon the vector of covariates here. That is an important assumption, which is not always justified. Okay, but I will comment on that at the end of the talk. If you make that assumption, you can write down what is the contribution for one data point on your likelihood. You have to, you can write that down mathematically. I'm not taking, it's a few lines, it's not more. But for an uncensored observation, so when delta I is equal to 1, the contribution to the likelihood of a data point is given by this. Where F is the, well, this is the conditional density of T given X, the capital G and the small g are the conditional cumulative distribution function and density function of the censoring time given the covariates. If you write down the contribution of observation when it's a censored observation, then you get this contribution. If I put everything together in one line, so instead of writing two lines, I write one line, but then I write the delta I. So when delta I is equal to 1, I have this contribution. When delta I is equal to 0, I have this contribution. So if I would write down the full likelihood in this setting for all my data points, then you would end up in this, including the red part here. But then there is a second assumption, which is often made in survival analysis, that is that the censoring is non-informative for the survival time. And this essentially means that in the likelihood, you can leave out the parts which refer to the censoring, the conditional censoring distribution, the small g and the g. If you leave that out, you get to this. And then I can, of course, use the relationships that I had between density and the hazard function, and you can express everything in terms of the conditional hazard function and the conditional survival function. So that would be like the kind of pseudo likelihood which you would work with. So that's again the same. Usually you work with a log likelihood because that's a bit simpler to work with. So I take the logarithm of this, so you go from a product to a sum. You get this, and then at this point, because so far this was very general, not imposing any kind of model, only making these two assumptions, now I bring in my hybrid hazard regression model, which tells me a kind of modeling for this, which tells me the kind of modeling for that, because I can translate, and this ends up, by this expression, which is at the end of the slide. So I'll come back on this because it's the same. So what are the parts that are unknown and not given by the observations? So the observations are delta I, yi, x1i, x2i, because these are the subfactors of x. The theta is unknown, that's the parameter of the baseline hazard function. And these functions, I have to see what to do with that. Now, important is that you can still consider various settings, in the sense that maybe you are convinced that the effect of the covariates let's say x1 on the time scale of the baseline covariates is parametric, you are convinced that there they come in linearly for some reason or another reason. You could maybe also be convinced for other reasons that the effect of the covariates on the relative errors is also parametric, for example, linear, or can also be quadratic, but I mean a parametric model. You can have maybe that you don't know what's the effect of the covariates on the relative hazards. You can do this non-parametric. There are various other settings. For example, maybe you are convinced that one covariate should really come in a linear way in this relative hazard, and then of course you can model it like that, whereas maybe another covariate comes on in a non-parametric way. So there are various settings which you would like to work with. And what I'm going to do today is not discussing each of these, but what I will discuss to you is actually the first and the second one, because then I hope you get the idea of how we do all the rest, actually, right? Okay, so let me explain that to you. So I take the simplest setting, right? Where you have parametric linear in both the time scale of the baseline covariate and the relative hazard. And I allow for this flexible baseline hazard model where I do have the parameter theta. So now I'm working fully parametric, right? There is the vector theta from the baseline hazard function. There is the beta one from here. There is the beta one from there. So I put that in one big vector of parameters, which I call theta p. Okay, the log likelihood depends on this theta p, and I can simply maximize it with respect to this. And you get your estimators, and you get your estimated conditional hazard function, conditional survival function, etc. Of course, this maximization problem might sometimes not be easy to solve. So I'm even not discussing about that, but I mean, we are the software that we have written can deal with many of the situations. Okay, what happens now if I now pass to a non-parametric part there? So this is an unknown function. I don't know whether it's linear, quadratic, cubic, sinus function, or whatever you can think of. I have no clue what would be a good parametric model. So there are various ways, of course, of dealing with that. There are various smoothing techniques, I would say. You can use splines, you can use wavelets, you can use local modeling, which is what I'm going to do here. And so suppose that I want, and for simplicity of presentation here on the slides, I only consider that covariate x2 is actually univariate, because then I can easily write down things and explain it to you. Suppose so that I want to estimate psi2 in a one-dimensional univariate setting here for a given value of x, and for an observation x2 which is close to that x, you can do a Taylor expansion, right? You can write psi2 of x2 as psi2 of x, because x2 is close to x, and I can take, I mean, if I would do a linear approximation, I would stop here, but I can generally write that down for a Taylor expansion of order p. Recall, all these things are unknown, so psi2 of x, psi2 prime of x, the pth derivative of psi2 divided by p factorial is unknown. All these unknowns I put in a vector which I call b2. Be careful, that depends on the x, but I'm not writing the dependence on the small x for not making the notation too heavy. All the rest, the one, that factor, I put in a vector x tilde 2, which I know, which I observe, right? And so essentially, when you now turn to your likelihood model, and I'll go back to my previous slide, where you have this. So this now, when x2 is in the neighborhood of that point x, I can basically replace this by its Taylor expansion. I only know that this is valid when x2 is close to the small x. So what I do is, instead of considering this global likelihood, I localize this likelihood by a kind of weight function over here, by a kind of weight function which is such that when my observation x2i is close to that small x, this weight should be high. when it's far away from this, my observation is far away from x, it should get weight 0. So think of this weight factor, for example, as being a normal density which has as a scale h. When h is small, your neighborhood is very local. When h is big, I'm actually back to my global modeling. And once you are in that neighborhood, I can actually approximate psi2 of x to I by effectively this for the ith observation. And that's what we do. And then, of course, be careful, the local weighted log likelihood function now depends on this x, right? So you maximize it, you determine what B2 is, and if you want to have the estimate of the function psi2, but also its derivatives in each, on the whole real line, if you want, you have to repeat this maximization problem for a grid of x values. And then you get the function psi2 estimated, but also all the derivatives, right? Of course, there is a parameter h coming in that you have to choose somehow, because that's the parameter that determines the local or the neighborhood, right? Or the local modeling, if you want. But so that's how you can estimate then the non-parametric part for given parametric part. But of course, there are the two parts, the non-parametric part and the parametric part, and we use a kind of steps procedure to change between them. So if you would give me the function psi2, no, let me say it differently. If you know the parameters, estimating psi2 would be done by maximizing this over B2 on a grid of x values, right? And if I know psi2, then you estimate theta p, your parameters, not by considering the local likelihood, but by considering the global likelihood. And you somehow swap between these two. So we have a 3 steps procedure. A first step is that we start from a given value of the parameters. I think you can obtain these parameters by just using Cox proportional hazards model, for example, or a simple model. Once you have these, you estimate the function psi2 as a whole function. Once you've estimated that function, you again then essentially get the estimates for the parameters from the global likelihood, and then you do a third step and the last step, which is you update basically the estimator for the non-parametric part, and that's it. And you can imagine that if there is now this also non-parametric, you basically do it in a similar way, right? So it's very similar to do it like that. Now, what about certain constraints? And let me maybe go back to the model that we assumed, which is here. Of course, this is parametric, right? Even if you leave this non-parametrically, you have to be careful with, you have to assume some constraints, right? You have to assume that this function in 0 is equal to 0. Why is that? Because otherwise you have any kind of arbitrary factor coming in here, which you could basically swallow up in the parameters of lambda b. So for identifiability, you really need to assume, well, one of the things you can ensure identifiability is that you assure that psi1 of 0 is 0 and psi2 of 0 is 0. Now, how do we impose that? There are various ways of doing that. We took a very, very simple way, in the sense that you, of course, know that psi2 of x is the integral of 0 to x from its derivative. And instead of taking the estimator which comes out of the procedure, we take the estimate for the first derivative, which we have in any case for free, and you then replace the estimator for psi2 by this one, because that's always 0 and 0. That's guaranteed to be 0 and 0. So you have that for free. Of course, you need to take care of calculating this integral, but for that we use just some known procedures from numerical analysis, essentially. Okay, I don't know what's the time, but I have to pay attention to that.
Yes.
So I have a couple of slides. Maybe I'll skip this one. I'll skip the testing procedure. Let me immediately go to the real data application. It's one real data application that I want to show you. It's data about lung cancer, which they cannot operate anymore. It was a study which involved 137 patients. Only 9 actually survived at the end of the study, which is of course sad. But this means that the percentage of censoring was quite low. And what is of interest in the study is the survival time, which is the time to death in days for patients. Of course, you want to tell them their prognosis if you want. Covariates in this study, which were set up as potential important, was, for example, the age and years of the patients, was whether their treatment was standard or it was the testing procedure, the time gap between diagnosis and the start of the treatment was another covariate, whether there was prior therapy or not was a covariate. And let me now come to the covariates which in fact are most important. That is a kind of Karnofsky score, is a kind of score which measures the patient's performance. They have to, it's basically measuring the lung function, let's say, of the patients on a scale from 0 to 100, where 100 is the best performance, and also the type of cancer. Lung cancer, the prognosis very much depends on the type of tumor cells. And so these were the covariates, and essentially this data have been analyzed beforehand, of course, among others, using a proportional hazards model, penalized versions of that, proportional odds model. And when you look at these analyses, there were 2 things which basically came out as quite statistically significant as covariate. That was the Karnofsky score and one of these cell types. So the adenotype cell versus large cells. All the others were like non-significant. Now I'll just show you a simple analysis of our methodology. In the paper you find more information. We used the log link here. We used for F0 only, I just present you result for 2 reference, symmetric reference density, which is a normal one and logistic one. So these are these 2 lines. We fitted actually a proportional hazards model, accelerated failure time model, an accelerated hazard model. Maybe only look at this for the moment. And when you use a model selection criteria like ICAIC's information criteria, which takes into account parameters in your model, the one that came out best of all these, putting in all the covariates in a linear way, so starting very simple, the one which came out best was actually an accelerated failure time model with this as the smallest AIC value among these 6. Now, what is important is also that in terms of statistical significance, that what we found was also whether the tumor cells are of this small cell type or not was also coming in as being important. I'll now go to the next slide first. Yeah. So what we then also did was allowing that the covariates come in a different way in this time scale of the covariate function and in the relative hazard. And it appeared that this is actually important. Look at the drop at the AIC value, which you get. So the green one is actually the lowest one in all these numbers. And without that I explain you too much, I'll here show you in this table the estimated parameters for the baseline hazard, that's this. Then you have the estimated parameters for the effect on the time scale of the hazard function, that's this, and this is on the relative hazard function. And these are standard errors that we could calculate using, some of the methods that we developed. But important to note is that the things that are indicated with a star means these are the covariates which are significant actually. And you see that the values, that the variables that are significant on the 2 different levels are not the same. And essentially you see the Karnofsky score is actually coming in on the 2 levels, but actually which kind of type of tumor cell actually plays a different role on the hazard function. And that was nice to see. And just to show you that this kind of study, and that's my almost last slide, Italia, that is that this graph just shows you the estimated or the predicted survival functions for two types of patients. Patients which have a certain cell type, which is the same for both, but their Karnofsky score is different, right? So the patient with the solid line has the lowest Karnofsky score, and the other one has a higher Karnofsky score, so essentially is in a better shape. And you see that the prognosis for the survival time or the predicted survival time is quite different for both patients. If you think of having a time surviving up to 150 days, you see that it's quite different probability of surviving for the two groups. And of course, it's important that this estimation of these conditional survival probabilities is done as accurate as possible, taking into account the covariates that basically play a role. Okay, this then I can summarize what I tried to explain to you. So I started by recalling these known proportional hazard and accelerated failure time models, indicating that they are quite a simplification and showing how essentially you can bring in more flexibility in these models while still keeping the same kind of interpretation, which is important. And well, I skipped the testing thing. Maybe it's interesting to mention that R codes have been written to do all this. There is an extensive simulation study, which I didn't show you at all, which is available in the paper. Theoretical results, they have not been established yet, but since we have been working with these two-piece distributions in other setting and the local likelihood in a different context, we are pretty sure that this would work out, but we still have to do it. Data-driven choices of the parameter H has to be done. And another important thing which we would like to do in future is that we would like to drop the assumption that the survival time and the censoring time are conditionally independent. And there, I would like to do this with Copla modeling, but I know this will be a work of several years because it's not so simple. So thank you very much for your attention, I would say, and I'll just show you some references.
Thank you, Irène, for this impressive job that you have done. And there are several questions. Okay. The first one is from, what is happening? A moment. If understood, Claudia asked, if understood correctly, the subset of variable x1 in the baseline hazard and those in the exponential part are known a priori. I mean, you are not doing a variable selection, right?
Well, I think that's an excellent question. We are not doing variable selection because you could do that, but in a sense, if you would take just take your full set of covariates and you allow the beta 1 and the beta 2, you could actually do it like that, right? The covariates that, which is what I showed you in the data example, actually. So we put all covariates in there. And essentially, we let it run, and we see which of the covariates are significant for which part, right? So you estimate beta 1 and beta 2 separately. Of course, if you have you could do model selection in this setting too, because if X is big, you could essentially do model selection also on the different parts. But we didn't do that in so far, but I think this is a very interesting question, absolutely. But we didn't do it. We avoided it by simply taking x1 to be equal to the full set and x2 to be equal to the full set. Because in this data examples, we didn't have an idea which one comes in where. But you could do actually a variable selection. I'm pretty much sure in this context. Thank you for the question.
Indeed, what you have told is connected to the second question, where Daniel asked, First, thank you for the beautiful talk, and then ask if you could spend some words for a possible penalization approach we could use when maximizing the likelihood.
Yeah, so essentially, if you would take, we do have an expression of a likelihood, right? Which contains this parameter theta from the baseline hazard and the parts from the psi1 and psi2. If you want to do, like, let's, for example, do variable selection, you put in a penalty function with the log likelihood, as you usually do. As soon as you have a log if you have a likelihood or a logarithm of the likelihood, you can add a penalty term, right? A penalty term where you maybe want to say, okay, I want to have I want to penalize if you express, for example, your psi1 in terms of a spline functions, you want to have only a small amount of coefficients that are different from 0. That would be penalization, right? And that's the way how you would bring it in that case, if you would penalize. The same for variable selection. If you would use lasso in that context, you would do variable selection. So you could do it you could do it separately for the two parts by bringing in two penalties. So that's a bit, or you could, it depends, huh?
Yeah. Then there is always by Claudia. I miss how did you test the significance of the covariates, since the same covariate may appear in the baseline and the exponential part. Could you please explain again?
Well, this is, that's actually what we do there is really going back to this idea of having the different steps in the estimation procedure, right? When you are in a step where you estimate like the part which concerns the time scale of the covariate, how to say that, you basically can split, well, let me say differently, you can, due to the choice of also this baseline hazard function, all the estimation of the parameters in some sense end up to be orthogonal to each other. So it's like you have separate submodels in there. And that's why you can essentially consider the significance of the covariates in the different parts actually independently. And this is the nice thing about this kind of modeling, I think. Of course, the full theoretical support for that we still need to do, but that's the beauty of I would say this way of working, is that it actually all is factorized in different parts, right? The part that comes in the baseline, the part that comes in this time scale covariate, and the part that comes in the relative hazard. As in for accelerated failure time models, you also have that. It ends up like that. I hope that this is clearly explained. So you focus, yeah.
Okay, thank you, Irène. There are no more questions. So we thank you again, our guest, and we hope to see you in September with a new series of seminars. Bye-bye to everybody.
Thank you, Ilaria.
Thank you.